In electrochemistry, we have two types of electrochemical cells, those being a galvanic cell, where we're converting chemical energy into electrical energy spontaneously, or an electrolysis cell, where we're pumping electrons through an external circuit to actually store chemical energy. So this question here is a case where we have an electrolysis cell, so we're using an external energy source to convert electrical energy into stored chemical energy. So how do we do that? We use a battery, and there's the battery symbol there, and a battery always points in the direction of electron flow, so it's sort of pointing in that direction, so that means electrons are flowing in that direction there. So what does that mean for our electrodes? Which electrode is giving up electrons and which electrode is receiving electrons? So the left-hand electrode here is actually getting electrons stolen from it by the battery, by the pump, the electron pump, and the right-hand electrode there is getting electrons pumped to it. So what's happening at the surface of the electrodes is copper metal atoms are giving off their electrons there and actually dissolving off. So we're actually getting this electrode actually dissolving. Those copper ions are moving across to the other electrode, and on the other electrode there's too many electrons. Those electrons are able to reduce those copper ions and precipitate copper metal on the surface of that electrode. So what we find is the left-hand electrode here gets smaller and smaller and smaller, where the right-hand electrode actually grows. So this is a way to purify the metal. So we're transferring mass from one side to the other. How is that happening? Well, we have the chemical reaction below there, and the chemical reaction shows us the stoichiometry of the reaction because of the number of moles of copper ions there divided by its stoichiometric coefficient 1 is equal to the number of moles of electrons there divided by its stoichiometric coefficient 2, which is equal to the number of moles of copper metal atoms that are formed on that electrode divided by 1. So to do this, we need to do this question, to work out the mass of copper that's transferred, we need to work out the number of moles of copper that are formed, and then the mass of that is equal to the number of moles divided by relative atomic mass. So first of all, we have to work out how many moles of electrons are transferred in this case. So the way that we can do that is we can think about the charge on one individual electron. And the charge on an electron is equal to minus 1.6 by 10 to the minus 19 coulombs, and coulombs is the SI units of charge. We can also think about Avogadro's number, which is the number of particles in 1 mole of something. So Avogadro's number is 6.02 by 10 to the 23. And if we multiply these two numbers together, we can get the charge totally on 1 mole of electrons. When we do that, we call that F, we give it the symbol F, and that is 96,485 coulombs per mole, which is Faraday's constant. We call it Faraday's constant. So now we can work out the charge on 1 mole of electrons, but we still don't have the amount of charge that's transferred here. So the quantity of charge that's transferred in an electrochemical cell, Q, is equal to the current times the time that we're actually transferring that current through the cell. And the SI units of current are amps, the SI units of time are seconds. So we can then work out how much quantity of charge is transferred here, 2.5 amps times 25 seconds. So in this case here, we have 62.5 coulombs of charge transferred. So we still need to work out the number of moles of electrons that are transferred. So the number of moles of electrons is equal to the quantity of charge divided by Faraday's constant, which is the charge of 1 mole of electrons. So 62.5 coulombs that we've transferred divided by 96,485 coulombs per mole will give us the number of moles of electrons that we're transferred, which is 6.5 by 10 to the minus 4 moles. We then know there's a stoichiometric relationship between the mass of copper that's actually formed on the right-hand electrode and the number of moles of electrons that are formed. If we substitute what we know about the number of moles of electrons, we can work out the number of moles of copper. So 6.5 by 10 to the minus 4 moles of electrons divided by 2 is equal to the number of moles of copper that are formed, which is 3.2 by 10 to the minus 4 moles. Now, the number of moles is not exactly half because I'm keeping the correct number of significant figures in my calculator. So then the mass of copper that's formed is the number of moles of copper times the relative atomic mass of copper, and that equals 3.2 by 10 to the minus 4 moles times by 63.55 grams per mole. So that equals 0.021 grams of copper that are formed on that other electrode.